This presentation is part 3 of liquid mixtures. Here, I shall briefly explain a system with lower critical solution temperature and a system with lower critical solution temperature and upper critical solution temperature. You shall also have a brief idea about the effects of solutes on binary liquid systems which are partially soluble. A brief recap of what CST is. The temperature at which two partially miscible liquids become completely miscible in all proportions is called the critical solution temperature or consolute solution temperature. Partially miscible liquids with lower critical solution temperature. The temperature at which and below which the two partially miscible liquids become completely miscible in all proportions is called the lower critical solution temperature, briefed as LCST. Triethylamine-water system is an example of LCST. The lower critical solution temperature for this system is 18.5 degrees Celsius. Diethylamine-water system has an LCST of 43 degrees Celsius. Methyl piperidine water system has an LCST of 48 degrees Celsius. Let's take the example of triethylamine water system. The figure that you see is a temperature composition curve for this system. To the extreme left is 100% water and to the extreme right is a curve showing 100% triethylamine. Mutual solubility decreases with increase in temperature. The left-hand side of the curve shows the solubility curve of triethylamine in water, while the right-hand side of the curve is the solubility curve of water in triethylamine. The two conjugate solutions merge to form one layer at 18.5 degrees Celsius, and this is called as the lower critical solution temperature. So for triethylamine water system, the lower critical solution temperature is 18.5 degrees Celsius at a composition of 50% each of water and triethylamine. Above the curve, we have two layers existing, and below the curve, we have only one layer. Partially miscible liquids with both upper CST and lower CST. Nicotine-water system with UCST 208 degrees Celsius and LCST 61 degrees Celsius. Glycerin metatoluidine system with UCST 120 degrees Celsius and LCST 7 degrees Celsius. And another example of water and beta-picoline system with UCST 153 degrees Celsius and LCST 49 degrees Celsius. For this category of critical solution temperature possessing both UCST and LCST, let's take the nicotine-water system. At ordinary temperature, nicotine and water are completely miscible. At a higher temperature, the mutual solubility decreases, and as the temperature is raised further, the two liquids again become miscible. This system has 2 CST, an upper critical solution temperature of 208 degrees Celsius and a lower critical solution temperature of 61 degrees Celsius with composition 34%. Excuse me. This is a closed solubility curve. Inside the curve, we have 2 layers, and outside the curve, we have only 1 layer. Effect of addition of non-volatile solute on critical solution temperature. CST varies almost linearly with the amount of soluble impurities. If an impurity is soluble in one of the 2 liquids, CST of the system increases. For example, 0.1 molar naphthalene dissolves only in phenol and raises the CST of phenol water system by about 20 degrees Celsius. 0.1 molar potassium chloride dissolves only in water and raises the critical solution temperature of phenol water system by about 8 degrees Celsius. If an impurity is soluble in both the liquids, the critical solution temperature of the system decreases. Sodium oleate decreases the critical solution temperature of phenol water system. A summary of what we just went through. UCST and LCST systems, mutual solubility and temperature curves, LCST of triethylamine-water system, UCST and LCST of nicotine-water system, and the effect of impurities on the critical solution temperature.